Good morning, everyone. This is an audio recording for visually impaired student. Today, I am going to read a chapter from Pradeep Organic Chemistry written by Dr. S. N. Dhawan. Chapter Diazonium Salt. Introduction. Diazonium salt were discovered by John Pater Graces in 1858. They have the general formula Ar N2 positive X negative, where Ar stands for the aryl group and X may be any anion such as Cl negative, Br negative, NO3 negative, HSO4 negative, BF4 negative, etc. Aliphatic diazonium salts are also known, but they are highly unstable. They rapidly decompose even at a low temperature, forming carbocation and nitrogen gas. Rn positive triple bond NX negative, it will give carbocation plus N2 plus X negative. Therefore, in this unit, we shall discuss the chemistry and synthetic application of arene diazonium salt, only particularly with reference to benzene diazonium chloride. Nomenclature. Diazonium salts are named by adding the suffix diazonium to the name of the aliphatic compound followed by the name of the anion. For example, benzene diazonium chloride, P-toluene diazonium hydrogen sulfate, P-nitrobenzene diazonium fluoroborate, P-chlorobenzene diazonium bromide. Structure of benzene diazonium chloride. Molecular formula. The molecular formula of benzene diazonium chloride as determined from the analytical data and molecular weight determined is C6H5N2Cl. Second, crisis structure. Crisis structure proposed for benzene diazonium chloride in which both the nitrogen atom were directly linked to the benzene nucleus. This structure, however, failed to account for the following fact. Its salt-like character. Second, displacement of both the nitrogen atom by a univalent atom or a group in most of the reaction. C6H5N2Cl, it will give C6H5X. X may be HOH, OR, Cl, bromine, iodine, Cn, etc. Third, its reduction to phenylhydrazine in which only one nitrogen is attached to the benzene ring. C6H5N2Cl in the presence of SnCl2 or Na2CO3, it will give C6H5NH2, which is called phenylhydrazine. Formation of azo compound by coupling reaction. C6H5N2Cl in the plus C6H5Y, it will give azo compound. Formation of aromatic diazonium salt from pentasubstituted aniline. 2,3,5,6 tetrabromosulfonic acid in the presence of NaNO2 HCl at 273 to 278 Kelvin. It will give 2,3,5,6 tetrabromo 4 sulfobenzene diazonium chloride. Third, Kekulé structure. Kekulé proposed structure second for benzene diazonium chloride in which only one nitrogen was linked to the benzene nucleus. C6H5 and double bond NCl. Evidence in favor. Structure second explain most of the drawback of gaseous structure, such as its reduction to phenylhydrazine, formation of azo compound by coupling reaction, preparation of diazonium salt from pentasubstituted aniline, and displacement of both the nitrogen atom by a univalent atom or a group. Point against Kekulé structure. Structure second cannot explain first its salt-like character and its instability as compared to azo compound since both contain N double bond and linkage. Fourth, Bloom-Strand structure. Bloom-Strand suggested structure third for the benzene diazonium chloride in which the nitrogen attached to the benzene ring is pentavalent while the other is trivalent. C6H5 N positive triple bond and Cl negative. Evidence in spot. It explains all the objection of structure first and second. Structure third is further spotted by the following fact. Its ready solubility in water but not in common organic solvent. Its complete ionization as shown by conductive measurement. The presence of a triple bond as shown by the infrared spectroscopy. Its instability as compared to azo compound. It's explain the geometrical isomerism as shown by the diazotes as or diazotes, which are metallic salt of the diazonium hydroxide. Benzene diazonium chloride, in the presence of NaOH, it will give benzene diazonium hydroxide. In the presence of NaOH, it will give benzene diohydroxide. In the presence of NaOH, it will give sodium benzene diazoate. If it will get reversed in the presence of HCl, then the reaction will get reversed. The sodium benzene diazide can exist a pair of the geometrical isomerism due to hindered rotation about the N double bond end bond. It may be sine form and it may be antiform. Preparation of diazonium salt. Aromatic diazonium salt are generally prepared by adding a cold aqueous solution of sodium nitrite to the solution or suspension of a primary aromatic amine in an acid at 273 to 278 Kelvin. Primary amine in the presence of NaNO2 plus 2HX, it will give arene diazonium salt plus NaX plus 2H2O. For example, C6H5NH2 plus NaNO2 plus 2HCl in the presence of 273 to 278 Kelvin, it will give benzene diazonium chloride plus NaCl plus 2H2O. Diazonium salt are also formed when aromatic primary amine react with nitride ester such as amyl nitrite. The nitride ester needed for the purpose are prepared by treatment of alcohol with nitrous acid. Thus, amyl alcohol plus HNO2 it will give amyl nitrite plus water. The process of conversion of a primary aromatic amine in its diazonium salt is called a diazotation. General procedure for diazotation: the primary aromatic amine is dissolved or suspended in a dilute acid such as HCl H2SO4. 3 moles of a acid are generally used for every mole of a amine to be diazotized. 1 mole to form the salt of amine, 1 mole to liberate nitrous acid from sodium nitrite, and 1 mole to keep the reaction mixture acidic enough to suspend the undesirable side reaction, such as the coupling of the diazonium salt, thus formed with the free amine. The amine solution is cooled and a cold aqueous solution of sodium nitrite is added slowly to it at such a rate that the temperature of the reaction mixture does not arise above 278 Kelvin. The addition of sodium nitrite solution is stopped as soon as few drop of the reaction mixture produces a blue color with a starch potassium iodide paper showing the presence of unreacted nitrous acid in the reaction mixture. Too much excess of nitrous acid is generally avoided since it subsequently interferes with the reaction of diazonium salt. The excess of nitrous acid may be destroyed by addition of urea plus 2HONO. It will give 2N2O plus CO2 plus 3 mole of H2O. Since diazonium salt slowly decomposes even at low temperature, about 273 to 278 Kelvin, they are used immediately after preparation. Mechanism: the diazotation of amine is followed, believed to occur by the following mechanism. Evidence in spot. This mechanism is spotted by the observation that aromatic amine containing electron withdrawing group such as NO2 are less easy to diazotized. This is due to reason that the nucleophilic of the amino group is reduced due to the electron withdrawing effect of the NO2 group as shown as. Such amines can, however, be diazotized in acetic acid. Conversely, aromatic amine containing electrodonating group at ortho and para position undergo diazotation much more readily than aniline. Stability of diazonium salt. Aromatic diazonium salt are much more stable than aliphatic diazonium salt due to the dispersal of positive charge over the benzene ring as shown below. Alternatively, the instability of diazonium salt is due to their tendency to eliminate an exceptionally stable molecule of nitrogen to form carbocation. Example: aliphatic diazonium salt, it will give alkyl carbocation plus N triple bond N plus X negative. Similarly, aromatic diazonium salt, it will give phenyl carbocation plus N triple bond N plus X negative. Since the phenyl or aryl carbocation is much less stable than alkyl carbocation, therefore, aromatic diazonium salt have much lower tendency to eliminate nitrogen than aliphatic diazonium salt. In other words, aromatic diazonium salt are much more stable than the aliphatic diazonium salt. Physical property. Diazonium salt are generally colorless crystalline solid, highly soluble in water. Many diazonium salt, especially especially nitrine, are dangerously explosive in a dry state. Therefore, they are never isolated but are usually prepared in situ and used immediately after their preparation. However, certain diazonium salt, such as fluoroborate, are relatively insoluble in water and are stable enough to be dried and stored. Some diazonium salt also form complexes with metallic salts such as zinc chloride, Ar N2 positive, twice ZnCl4 negative. These complexes are generally insoluble. Chemical property. Arene diazonium salt are highly reactive compound. Their high reactive arises due to excellent living ability of the diazonium group, such as nitrogen gas. They are therefore extremely useful synthetic reagent in organic chemistry. The reaction of diazonium salt are broadly divided into the two categories. A. The reaction in which the diazonium group is replaced by the monovalent atom or a group. B. The reaction in which the nitrogen atom are retained. A. Reaction in which the diazo group is replaced by the monovalent atom or a group. Some important reaction of this category along with their synthetic application are discussed below. First is the replacement by hydrogen de-emission. The replacement of a diazo group by hydrogen or the reduction of diazonium salt to arene is usually brought about by treatment of diazonium salt with hypophosphorus acid at room temperature, probably in the presence of copper salt as a catalyst. Arene diazonium salt plus H3PO2 plus H2O in the presence of Cu positive, it will give arene plus phosphoric acid plus HX plus N2 gas evolved. This reaction can also be carried out by treating amine with sodium nitrite and hypophosphorus acid as diazotation reagent. Alternatively, diazonium group may be replaced by hydrogen by heating arene diazonium saltate with ethanol, for example, arene diazonium salt plus CH3CH2OH. In the presence of heat, it will give arene plus N2 plus HX plus CH3CHO. These wall process involving the diazotation of an amine followed by reduction of the diazonium salt or replacement of the diazo group by hydrogen is called the deaminization. It may be emphasized here that during the reaction of diazonium salt with ethanol, two products are usually obtained. One involving the replacement of a diazo group by hydrogen as discussed above and another by the ethoxy group. Benzene diazonium chloride in the presence of CH3CH2OH, it will give phenolate, and in the presence of CH3CH2OH, it will give the benzene. The relative amount of the two products, however, depend upon the nature of the diazo compound and the alcohol used. If AI group is present in the nucleus and the ethanol is used, the replacement of diazo group by hydrogen predominated. If on the other hand methanol is used, the predominant product is aryl methyl ether. Example anisole. Benzene diazonium chloride plus CH3OH, it will give anisole. Mechanism. The reaction occurred by the free radical mechanism is illustrated below. Diazonium cation, it will give the aryl radical. Propagation, synthetic application. The importance of deamidation is illustrated by the following application. First, synthesis of the metabromotoluene. Synthetic of the metabromotoluene. P-toluidine in the presence of CH3CO twice of pyridine, it will give P-methyl acetonalide. In the presence of bromine, CH3COH, which is called bromination, it will give 2-bromo 4-methyl acetaldehyde. In the presence of 70% H2SO4 and heat, it will give 2-bromo 4-methyl aniline. In the presence of NaNO2 HCl at 273 to 278 Kelvin, which is called diazotation, it will give benzene ring with CH3 with 1 bromo and N2Cl negative N2Cl. And in the presence of H3PO2 water Cu2 positive, it will give M bromo toluene. Recall M-bromotoluene cannot be prepared by direct bromination of toluene or a Friedel-Crafts alkylation on bromobenzene due to the OP ortho-para-directing nature of the methyl group and the bromine atom. Second, synthesis of the 1,3,5 tribromobenzene or sim-tribromobenzene. Aniline with bromination, it will give 2,4,6 tribromoaniline. With the help of diazotation, it will converted into these compounds. And in the presence of CH3, CH2OH or H3PO2, it will give 135 tribromobenzene. Third, synthesis of the 3,5 dibromotoluene. P-toluidine in the presence of bromine CH3COH, it will give 2,6-dibromo 4-methyl aniline. With diazotation, it will converted into benzene with N2 positive HSO4 CH3 2 bromine, and in the presence of H3PO2 copper positive, it will give 3,5-dibromotoluene. Recall direct bromination of toluene with bromine 2 FeBr3 give 2,4-dibromotoluene. Second, replacement by hydroxyl group OH synthesis of phenol. Diazonium salt react with water in the presence of acid to form phenols. The reaction is generally carried out by adding the solution of diazonium salt to a large volume of boiling dilute sulfuric acid. Air N2 positive X negative with water in the presence of H2SO4, it will give phenol plus N2 gas plus HX. The acidic condition minimize the side reaction involving the coupling of phenol with diazonium salt. Mechanism. This reaction occur by SN1 mechanism as shown phenol. Diazonium cation, it will give phenylcation. After that, with the help of fast nucleophilic attack, it will give the phenol. Synthetic application. This reaction is especially important since only a few methods are available for the direct introduction of a hydroxyl group into the benzene nucleus. Synthesis of M-nitrophenol, M-nitroaniline in the presence of NaNO2, H2SO4 at 273 to 278 Kelvin, it will give benzene ring with N2 positive, HSO4 negative with NO2 in the presence of dilute H2SO4 boiling, it will give M-nitrophenol. Third is a replacement by halogen. Different methods are used depending upon the type of halogen to be introduced. First, the replacement by chlorine or bromine, Sandmeyer reaction. Aryl chloride and bromide can be easily prepared by treating a flesh prepared cold aqueous solution of an arene diazonium salt with a solution of cuprous chloride in hydrochloric acid or cuprous bromide in a hydrobromic acid. The reaction is called the Sandmeyer reaction and gives aryl halide in 60 to 8 yield. It may be noted here It may be noted here that it is the halogen which is attached to the copper which entered the nucleus. Mechanism of Sandmeyer reaction is believed to occur by a free radical pathway as delayed below. It is the halogen which is attached to copper which enter the nucleus. Mechanism of Sandmeyer reaction is believed to occur by a free radical pathway as delineated below. CuCl plus HCl, it will give CuCl2 negative plus H positive. Diazonium cation, it will give cupric chloride. After that, it will give the cuprous chloride plus chlorobenzene. Gattesman's reaction. It is a modification of the Sandmeyer reaction in which the copper powder and a hydrogen halide are used instead of cuprous halide dissolved in the corresponding hydrogen halide. Yield are often lowered around 40% than those of the obtained by the Sandmeyer reaction. Synthetic application. Synthesis of 1,2,3 tribromobenzene. P-nitroaniline in the presence of bromine CH3COOH, it will give 2,6-dibromo-4-nitroaniline. In the presence of NaNO2 H2SO4 at 273 to 278 Kelvin, it will give the benzene ring with bromine to bromine at ortho position and 2HSO4 and NO2 with Cu bromine HBr Sandmeyer reaction. It will give the 2,4,5 tribromonitrobenzene. After that, in the presence of SnHCl and NaNO2HCl, it will give 3,4,5 tribromobenzene diazonium chloride. In the presence of H3PO2 and Cu positive, it will give 1,2,3 tribromobenzene. B. Replacement by iodine. The replacement of diazo group by iodine does not require cuprous halide or cupr as a catalyst. It is simply achieved by treating a diazonium salt with potassium iodide or a solution of iodide in the potassium iodide. Uh, Ar and positive triple bond NCl negative plus Ki, it will give Ari plus N2 plus KCl. Synthesis of para-iodonitrobenzene, p-nitroaniline in the presence of NaNO2 H2SO4 at 273 to 278 Kelvin. It will give NO2 N2 positive HSO4 in the presence of I2Ki. It will give p-iodonitrobenzene. C. Replacement by fluorine Bell-Sisman reaction. When an aqueous solution of a diazonium salt is treated with fluoroboric acid, diazonium fluoroborate get precipitate out. It is filtered and dried. Unlike other diazonium salt, diazonium fluorobromate are fairly unstable compound. When dried diazonium fluorobromate is heated, it decomposes to produce aryl fluoride and boron trifluoride. For example, Ar N2 positive Cl negative plus HbF4, it will give diazonium fluoroborate. Ar N positive triple bond NbF4 negative. In the presence of heat, it will give aryl fluoride plus N2 plus boron trifluoride. Mechanism. The reaction occur by SN1 mechanism as shown below. Diazonium fluoroborate slowly release N2 and it will give aryl fluoride. Synthetic application. Synthesis of the fluorobenzene. Aniline in the presence of NaNO2 HCl at 273 to 278 Kelvin, it will give benzene with N2 positive Cl negative. In the presence of HbF4, it will give benzene diazonium fluoroborate. When heated, it will give fluorobenzene plus BF3 plus N2. For replacement by the cyano group, synthesis of nitrile. Aryl nitrile can be prepared by treating a diazonium salt with cuprous cyanide or potassium cyanide and copper powder. To avoid the loss of cyanide as HCl, the diazonium salt solution was neutralized with sodium carbonate and then treated with cuprous cyanide. Ar and positive triple bond NX negative. First neutralizes with N2CO3, second CuCN or KCN copper, it will give aryl nitrile. This reaction is called modified Sandmeyer reaction. Synthetic application. Since hydrolysis of nitrile gave carboxylic acid, therefore synthesis of the nitrile provided us with the excellent method for the preparation of carboxylic acid from nitro compound. For example, Toluene in the presence of HNO3 H2SO4 called nitration, it will give P-nitrotoluene. In the presence of FeHCl called the reduction or NaOH, it will give P-toluidine. In the presence of NaNO2HCl 0 to 5 degrees Celsius, it will give benzene with CH3 and 2 positive Cl negative. Neutralized with Na2CO3 or CuCN, it will give p-toluene nitrile. With hydrolysis, it will give p-toluic acid. Fifth, replacement by the nitro minus NO2 group. Nitro compound are generally prepared by treating a arene diazonium fluoroborate with an aqueous solution of sodium nitrite in the presence of copper powder. Benzene diazonium chloride in the presence of HBF4, it will give benzene diazonium fluoroborate. In the presence of NaNO2Cu, it will give nitrobenzene plus N2 plus NaBF4. Sixth, replacement by a arsenic acid ASO3H2 group called the Barrett reaction. Treatment of an arene diazonium salt with sodium arsenic in the presence of copper sulfate followed by acidification give an aryl arsenic acid. For example, benzene diazonium chloride plus Na3ASO3. It will give C6H5ASO3Na2. In the presence of 2 mole of HCl, it will give phenyl arsenic acid plus 2 mole of NaCl. Seventh, replacement by an aryl group called the Gomberg-Bechmann reaction. When an arene diazonium salt is treated with an aromatic compound, liquid or as its solution in an inert solvent if solid, in presence of an aqueous alkali by allyls are formed, yield are usually less than 40%. For example, B bromobenzene plus C6H6 in the presence of NaOH, it will give P bromodiphenyl have 35% yield plus N2 plus HCl. Mechanism: the reaction is believed to occur by free radical mechanism. In alkaline, sodium diazonium salt are converted into the corresponding azo compound which decomposes to produce aryl radical. B. Reaction in which nitrogen is retained. First, the reduction to aryl hydrazine. Arene diazonium salt upon reduction give good yield of the aryl hydrazine. This reduction can be brought about by a number of reagents such as the stannous chloride, hydrochloric acid, sodium sulfite, sodium hydrosulfite, and even electrolytically. If, however, strong reducing agent such as ZnHCl is used, the product is an aromatic amine. Benzene diazonium chloride react in the presence of ZnHCl, it will give phenylhydrazine. After that, it will give aniline plus ammonia. Mechanism of reduction of diazonium salt with sodium sulfide. The reaction probably occurred through nucleophilic attack by the sulfur atom of the sulfide ion on both the nitrogen atom, forming the dianion of hydrazine sulfonic acid, which is then converted into the hydrazine in the presence of acid. Second is the coupling reaction. Arene diazonium salt with highly reactive electron rich aromatic compounds such as phenol and amine to form brightly colored azo compound AR and double bond and AR. This reaction is called the coupling reaction and is extensively used in the azo dye industries. Whereas coupling with phenol occur in basic medium having pH 9 to 10, that of the amine occur in faintly acidic medium pH 4 to 5 at 273 to 278 Kelvin. Benzene diazonium chloride plus phenol in the presence of OH negative pH 9 to 10 at 273 to 278 Kelvin, it will give para hydroxyazobenzene, which have the orange color. Benzene diazonium chloride with aniline in the presence of H positive with pH 4 to 5 at 273 to 278 Kelvin, it will give diazoaminobenzene. After that, H positive heating rearranges, it will give P amino azobenzene, which have the yellow color. Coupling usually occur at a para position with respect to OH or NH2 group. If, however, the para position is blocked, it occurs at all the ortho position. For example, benzene diazonium chloride plus p cresol, it will give 2-phenyl azo 4-methyl phenol. If a compound containing both an amino group as well as the hydroxyl group at para position with respect to each other, then the orientation of the coupling reaction can be changed by changing the pH of the medium. For example, para aminophenol in the presence of C6H5 and 2 positive cell negative OH pH having 9 to 10, it will give 4 amino 2 phenyl azophenol, and in the presence of C6H5 and 2 positive cell negative having pH 4 to 5, in the presence of H positive, it will give 4 amino 3 phenyl azophenol plus HCl. The well-known indicator methyl orange, which is widely used in acid-base titration, is obtained by coupling the diazonium salt of sulfanic acid with N and dimethyl aniline. Sodium salt of sulfanic acid in the presence of NaNO2 HCl at 273 to 278 Kelvin, it will give benzene ring N positive double bond and Cl negative. After that, in the presence of N and dimethyl aniline, it will give methyl orange plus HCl. Mechanism of coupling reaction. The coupling reaction between benzene diazonium chloride or the phenol or a amine is an example of electrophilic substitution reaction in which the diazonium ion act as a electrophile where phenol or amine act as a nucleophile. A coupling with phenol. Since benzene diazonium ion are only weakly electrophilic, therefore strong nucleophile are needed for the reaction to occur. Further, since phenol is weakly nucleophilic but phenoxide ion is strongly nucleophilic, therefore coupling reaction of phenol are usually carried out in the alkaline medium. Benzene diazonium chloride, it will give benzene and double bond N with benzene ring double bond O, it will give para-hydroxyazobenzene. Role of pH. pH of the medium play an important role in the coupling of phenol. As stated below, the coupling of phenol is carried out in a weakly basic medium as explained above. In the alkaline medium, the diazonium salt first formed diazonium hydroxide, which immediately rearranged to diazohydroxide, which further react with alkali to form the corresponding salt called the diazate. All these three species in fact exist in equilibrium as shown below. Benzene diazonium chloride, it will give equilibrium with diazonium hydroxide. Rearranges, it will give diazohydroxide, and after that it will give sodium diazoto, does not couple. Since at high concentration of OH negative ion, the equilibrium will shift in favor of diazohydroxide and the diazide, both of which do not couple. Therefore, for the desired coupling reaction is to occur, the pH must be kept as low as possible in the alkaline medium. However, at a too low pH would suspend the dissociation of phenol to phenoxide ion. Therefore, to carry out the coupling reaction, an optimum pH is needed. In actual practice, the optimum pH for such coupling reaction is between 9 to 10. B. Coupling with amine, tertiary amine. The mechanism of coupling reaction of benzene salt with tertiary amine is similar to that of the phenol, except that this coupling is carried out under weakly acidic condition. C6H5 and positive triple bond and Cl negative plus N and dimethyl aniline in the presence of pH 4 to 5, it will give P, N and dimethyl amino diazobenzene. C. Reaction with primary and secondary amine. Coupling of diazonium salt with primary or secondary amine occur in neutral or mildly alkaline medium. Here, NH2 group of the amine first attack the diazonium cation to form the diazonium aminobenzene. However, when the diazoaminobenzene thus formed is heated in the presence of acidic medium, it undergoes diazoamino azo rearranged to form P p-amino isobenzene by the following mechanism. Role of pH. In the presence of high concentration of H positive, the lone pair of electron on the N2 negative accept as proton. As a result, the amine exists predominantly in the protonated form as shown below. Aniline, in the presence of H positive, it will give the aniline ion. Due to the presence of a lone pair of electron on the nitrogen atom, the amine is no longer nucleophilic and hence the coupling reaction will not occur at a high concentration of H positive. For example, low pH further, as explained above, to highly alkaline high pH also not favor coupling reaction by forming diazohydroxide or diazotase salt in significant amount. Therefore, an optimum condition pH of 4 to 5 is employed for such coupling reaction. Thank you.